Today we're going to continue talking about random number generation. So let's formalize the problem a little bit. So in this problem, I'm going to have a bunch of players. Let's say I have n players. And these players are externally owned accounts or maybe also smart contracts who are going to take part in my smart contract, in my protocol that I'm going to design. And then the goal is to generate a random number. So I want to generate a random number. I'm going to call this R. And I want it to be in the range from 0 to m minus 1. So I have m different values. And I need several really important properties here. So one property I need is to make sure that this random number is chosen uniformly. Okay, so I want to make sure that R is chosen uniformly, which basically means that for every I in this set, in the set of numbers from 0 to m minus 1, I want the probability that my random number happens to be I to be exactly 1 over m. Okay. So this is a very important thing. But of course, I also want to have consensus, because if I just needed a uniform random number, I could tell each one of the players to pick one uniform random number for themselves. But of course, the really important point here is that everyone agrees on R. And this is not too hard in the sense that if I save R in my smart contract, because everyone is reaching a consensus about everything in the smart contract, everyone will have the same value of R. So the way I'm reaching consensus on the generated random number is just by saving it in my smart contract. Now, I also want everyone to be able to participate in the generation of R. Okay. So I have these n players, and I want each one of them to be able to basically contribute a share to the generation of R. Now, in order to achieve that, I'm going to just require that every player I chooses some random number, chooses Ri, and then I'm going to also require that we have our final number R be the sum of the Ri's. And I'm going to take this sum modulo m. Okay. Now, why am I requiring this? Because this will give me a bunch of other really nice properties. For example, this property that even if I have one honest participant, even if I have one participant or one player who's choosing the Ri value uniformly at random, no matter what the other people do, the final R will also be distributed according to the uniform distribution. So this requirement actually helps me satisfy this one as well. But I also want some more nice requirements. So remember that one of the use cases I talked about was a lottery. And this is not necessarily just a lottery. This is just generating random numbers. And random numbers can have many other use cases as well. Someone wants to come in. Let me admit them. Yeah. So random numbers can have many other use cases as well. This is a more general problem than just lottery. And actually, we will see a simpler solution for lottery later on. We're just focusing on solving the problem of generating random numbers right now. Now, if you imagine that I want to generate this random number and maybe later use it for a lottery, of course, I want this random number to also be unpredictable. So what that means is before it is generated, none of the players should have any information about this R. So I want to say before R is generated, it is hidden from all of the players. So no player has any information about R. And of course, when I say they have no information, this is much stronger than saying that they don't know the value of R. I'm saying they don't know anything about R. For example, they cannot know that R is odd or even. They cannot rule out any of the values between 0 to m minus 1. Okay. Now, the other thing is that I want to also have tamper resistance, which means that no one can tamper with the result. Can tamper with R, so no one can change R or its distribution. So we talked about this in the last session. For example, if you have a commitment scheme and people are just committing to these values of Ri and then revealing the values of Ri, some people might decide not to reveal. And well, by not revealing, they're tampering with the value of R. They're changing the final value of R. And we said that if you change your protocol to say when someone doesn't reveal, I would just redo the protocol and I will restart everything, then they have successfully tampered with the distribution. So some values of R are going to have a higher probability now, and that's also not acceptable. Okay. So these are the requirements. And when I say no one can tamper with R, I don't mean just the players. I also mean anyone else. So maybe I have some other people on the blockchain who are just interacting with my smart contract. They're none of the players. They shouldn't be able to tamper. The miners, most importantly, shouldn't be able to tamper with the generation of R. So we have to keep track of all of these things. So this is what I want to do in this session. Now, how would you actually achieve this? So we had this protocol in the last session where every player would just commit to the RI, to their own share. And then at the end of it, when they revealed, we would just sum all of these up and we would say this is R. But the last problem we had at the very end of the previous session was that some players might not reveal. So what I need is a way of commitment that can be opened by the other players. I want to make sure that if I have an attacking player, if I have someone who's committed but is not revealing, then the other players can come together and they can reveal the value of this player. Okay. Now, how can I achieve this? Well, I'm going to talk about something called secret sharing. And initially, this might sound unrelated, but after we find a secret sharing protocol, we will go back and I will show you how it can help you with random number generation. So secret sharing is basically this problem. Suppose that Alice has a secret, and let's call this secret S. Okay. Again, in this course, whenever I'm talking about any variable and I don't talk about the type of the variable, you can think of it as a sequence of bits, which can be considered a number. It can be considered a string. So this S is a number or a string. It's up to you how you look at it. So let's say Alice has a secret S. And suppose that she has a bunch of friends. So let's say she has n friends. Let's call these friends friend 1, friend 2, to friend n. Actually, I want to use f for something else later on, so let me use phi. Friend 1, friend 2, to friend n. And she wants to basically share this secret between the friends such that if a lot of the friends come together, they can recreate the secret, they can find S. But if only a few of the friends come together, they cannot find any information about this. Okay. So if I want to formalize this, I say that Alice wants to give each friend I a share SI. So Alice wants to send some number Si to each of her friends, and I'm going to call that Si the share of that friend. And I want to have two requirements. The first property I like to have is that if T of the friends come together, and I will choose this number T as I like. So if T of the friends collaborate with each other, they can reconstruct S. They can find the secrets. Okay. And when I say T of the friends, I mean any T of the friends. So it doesn't have to be T specific friends. I have N friends. As long as T of them come together, they should be able to find my secret. And of course, the second requirement is that if there are T minus 1 friends, they shouldn't be able to do it. Okay. So actually, let me write it like this. I can write that any T of the friends who collaborate can find S. Okay. And then here, let's say no sets of T minus 1 friends can find any information about S. Okay, this is what I want to achieve. Now, how do you do something like this? I'm going to show you something called Shamir's secret sharing. It's named after its inventor, Shamir. And this is actually based on polynomials. So it's a very clever idea and also a very simple idea. So suppose that I have a polynomial. Let's say I have a polynomial of degree k. So let's say I have a polynomial p, and p of x is something like this. It's a0 plus a1x plus a2x squared, so on, to akxk. Okay. This is my polynomial of degree k. Now, suppose that I want to send this polynomial to you. How can I encode this polynomial? So the first encoding is to just use the coefficients, right? So if I just give you these values, a0, a1, a2, all the way to ak, I'm just giving you the coefficient of each monomial in this polynomial. This is a representation of the polynomial, right? But can I represent this polynomial in a different way? Well, actually, yes. A polynomial of degree k is uniquely determined by k plus 1 points. So if I just give you k plus 1 points that this polynomial goes through, that would also give you this polynomial uniquely, and it's a valid encoding. So this is my second encoding. I will just give you x1, y1, x2, y2, so on, to xk plus 1, yk plus 1. And what I'm telling you is that basically p of x1 is y1, p of x2 is y2, so on, and p of xk plus 1 is yk plus 1. Okay, so if I give you these points, if I give you basically k plus 1 points that this polynomial goes through, then this also represents a unique polynomial of degree k. Okay, and here I'm talking about polynomials over reals. Now, why is this the case? Let me just give you a very short proof of this fact. Actually, I can give you two different proofs now that I think about it. So here's the first proof. Suppose that I have a polynomial that goes through all of these points. Okay, I can then write a system of linear equations that basically use the coefficients of this polynomial. And that's going to be a system of n linearly independent equations. So it's going to give you exactly one solution. So if you've passed linear algebra, this would be pretty easy for you. So let me just give you an example. Suppose that I know my polynomial is of degree 2. Okay, so I say find a polynomial of degree 2. And when I say degree 2, I mean 2 and less than 2. So it might be degree 1. Find a polynomial of degree 2 that goes through 3 points. I'm going to give you this. I'm going to say, for example, it goes through 1, 2, it goes through 5, 1, and it goes through 6, minus 2. Okay, so I want to find the polynomial p such that p of 1 is 2, p of 5 is 1, and p of 6 is minus 2. I'm giving you 3 points. I'm saying find the polynomial of degree 2 that goes through these 3 points. Now, if I have a polynomial of degree 2, it's going to look like this. P of x is a0 plus a1x plus a2x squared. Okay. And I also know that P of 1 is 2. So what is P of 1? P of 1 is just a0 plus a1, because x is 1, plus a2. And I know that this has to be 2. I know that P of 5 is 1. What is P of 5? It's a0 plus 5a1 plus 25a2. This is 1. And I know that P of 6 is minus 2. So I have a0 plus 6a1 plus 36a2 is minus 2. Okay, so as you see here, I have 3 linear equations over 3 variables, a0, a1, and a2. And these are linearly independent, so I will have a unique solution. Now, I'm too lazy to solve this. So just give this to Wolfram Alpha or something to solve, and you'll get the values of a0, a1, and a2, and that gives you the unique polynomial that you were looking for. Now, the uniqueness of this polynomial, I can prove it by saying that these equations are linearly independent, and I have n equations over n variables, so I will find the unique solution. But there's also another way to prove the uniqueness of the polynomial. So let me just try this simple theorem. I want to say given x1, y1, x2, y2, so on to xk plus 1, yk plus 1. So given k plus 1 points, there is a unique polynomial p of degree at most k that goes through all these points. Okay. How do I actually prove this? Well, here's my proof. I say, let's prove it by contradiction. Let's suppose that there are several polynomials. Let's suppose that there are 2 different polynomials that go through all of these points. So let's take 2 of them. So let's say P and Q are 2 solutions. So 2 polynomials that go through all k plus 1 points. And additionally, let's assume that P is not equal to Q. Okay. So I'm going to just look at the result of subtracting these 2. So let's say I define F to be P minus Q. Okay. If F is the polynomial P minus Q, first of all, what is the degree of F? The degree of F can at most be K, right? Because the degree of P is at most K and the degree of Q is at most K. So I know that the degree of F is at most k. Okay, now what is f of x1? F of x1 is p of x1 minus q of x1. But p of x1 was y1, and q of x1 was also y1, because remember, both p and q went through this point, x1, y1. So f of x1 is 0. Okay. And similarly, I can say that f of x2 is 0, and so on. And f of xk plus 1 is also 0. Okay. So this means that the polynomial f has k plus 1 roots, at least. Maybe it has more, but it has at least k plus 1 roots. It has k plus 1 values of x, for which if I calculate f of x, it would be 0. Okay. But for those of you who've passed algebra, we're working in a Euclidean domain here. So basically what I mean here is that if f of x1 is 0, that means that f can be written of this form. It can be written as x minus x1 times something else. Let's call that g1. So this is just polynomial division, right? So I can divide f by x minus x1, and I will not have a remainder because f of x1 was 0. Okay. Now, f of x2 is also 0. So this means that f should be of the form x minus x2 times x minus x1 times something, right? And so on. And because I have k plus 1 of these, it means that f looks like this. It's x minus xk plus 1 times x minus xk, so on, times x minus x1 times something else. Okay? But the problem is that this part already has a degree of k plus 1. Or another way of looking at this is that if I have a polynomial of degree k, and this polynomial is not 0, it can have at most k roots. But this polynomial f has k plus 1 roots. This is a contradiction, so it means that f does not exist. And if there is no such f, then there cannot be two different polynomials p and q that go through all these points, which basically means that if I give you k plus 1 points, there is only one polynomial that goes through it. Well, actually, what I proved here is that there is at most one polynomial, but I will also give you a way of creating one polynomial, so you will know that there is exactly one polynomial going through. Okay. Now, how do we find a polynomial that goes through these points? So again, suppose that someone has given me these k plus 1 points. How do I find a polynomial that actually goes through this? And this is what we call Lagrangian interpolation. Okay. So the problem is this: given k plus 1 points, x1, y1, x2, y2, to xk plus 1, yk plus 1, find a polynomial p of degree at most k that goes through all of these points. Okay. Now, first of all, I'm going to create a polynomial that is 0 at all of these x values instead of except for one of them. Okay, so this is what I'm going to do. I'm going to define a polynomial, let's call it gi of x, and I'm going to say that this polynomial is just x minus x1 times x minus x2 times x minus x3, so on, times x minus xi minus 1, but then I don't add the xi. I then jump to x minus xi plus 1, and all the way until x minus xk plus 1. Okay? So I'm putting all of these. Actually, let me move this a little bit to the left. Okay. X minus xk plus 1. Okay. What is the value of this gi at x1? It's 0 because I have an x minus x1 here. What is the value at x2? It's also 0. The value is basically 0 at all of these x's except for xi, because I don't have x minus xi here. Now, I can additionally make it such that the value at xi is exactly 1. How can I do this? I can just divide this by whatever my value at xi is. So I can divide it by xi minus x1 times xi minus x2, so on, to xi minus xi minus 1, xi minus xi plus 1, so on, and xi minus xk plus 1. So if I create this polynomial has a value of 1 at xi, and it has a value of 0 at every other xj. Now, this is a weird way of writing this. I wrote it like this so that I give you the intuition on how I'm creating this polynomial. But actually, it's much easier to write it like this. I can just say that gi of x is the product over all j that is not equal to I of x minus xj over xi minus xj. Okay? And again, the really important property of this polynomial gi is that gi of xi is 1 and gi of xj is 0 for every j that is not equal to I. Okay? So great. I have a polynomial that takes a value of 0 at all the points except for x1 and takes a value of 1 at x1. I have a different polynomial that takes a value of 0 at all of these points except for x2, and at x2 it takes a value of 1, and so on. So I can combine these polynomials to get a polynomial that goes through all these points, right? So I can just say my polynomial p is simply define p like this. Define p to be, well, I'm going to take g1 and I'm going to multiply it by y1. So y1 g1 plus y2 g2, so on, to yk plus 1 gk plus 1. Now, what's happening? So consider the first point, for example, x1, y1. Why does this polynomial p go through x1, y1? What is p of x1? So p of x1 is going to be y1 times g1 of x1, but g1 of x1 was 1. So this is just y1. And then g2 of x1 is 0, g3 of x1 is 0, and so on. So all of these other terms will cancel out. So p of x1 is just y1. And then similarly, p of x2 is y2, and so on. And generally, if I look at p of xi, here all the gj's where j is not equal to I will be 0, and they will cancel out. And I will just have a yi times gi. And then gi at xi is 1, so yi times gi of 1 times gi of x1. What did I say? Yi times gi of xi is going to be 1. So this polynomial p has the exact properties that we're looking for. So I literally have a formula for how to create this polynomial. And of course, the degree of this polynomial is at most k. Because if you look at each one of these gi's, well, this thing that I'm dividing by, this is just a constant, right? This is a numerical constant. And in the numerator, I have k terms. So the degree of every GI is at most K. And so this P, which is a linear combination of polynomials of degree at most K, is also going to have a degree of at most K. So I know that the degree of P is at most K. So what do I have now? Basically, it's very simple. If I give you K plus 1 points, I showed you that there can be at most one polynomial that goes through them. And then I showed you how to create this one polynomial that can go through all of these points. So there is a unique polynomial of degree at most K that goes through these K plus 1 points. Okay. Now, when I was proving this, I was assuming that my numbers are real numbers. But calculations with real numbers are hard. And we prefer to do calculations modulo some prime number and use integers and so on. All of this works in those cases as well, as long as I have an underlying field. For those of you, again, who have passed algebra, this works. So instead of doing these calculations and theorems and so on over x and y values that are in R, I could say I have a prime number, and then I'm just using integers modulo that prime number, and all of these theorems would work exactly in the same way. Okay? Now that we have all of these polynomials and so on, let's go back to our secret sharing. Remember, Alice has a secret S. She has n friends. She wants to give each friend a share, Si. And if T of her friends come together and collaborate with each other, they should be able to find the secret S. But if there are fewer than T friends, even if you have T minus 1 friends, they shouldn't be able to find any information on S. Okay? So how am I going to use polynomials to get this? So this is Shamir's secret sharing, and it's, again, very clever and very easy. So here's the idea. I say that in step 1, Alice creates a polynomial. Okay. So she's going to create a polynomial, and let's call this polynomial f, and f of x. This is going to be a polynomial of degree t minus 1. So it's going to be of the form a0 plus a1x plus a2x squared, so on, to a t minus 1 x to the power of t minus 1. Okay. Now, Alice would put her secret in A0. This is the secret. Okay. So Alice chooses A0 to basically be her secret S. Okay. So immediately this would mean that f of 0 is the secret. Right, because f of 0 is just a0. If x is 0, all of these things cancel out, and f of 0 is the secret. Okay. Now, after she does this, she's going to choose just random numbers for a1, a2 to at minus 1. So Alice chooses all of the other coefficients, a1, a2 to at minus 1 randomly. Okay, this is the polynomial that she's creating. But very importantly, I want all of my calculations to be modulo a prime number p. I don't want to work with real numbers. So I can say at the beginning, maybe this is like step 0. I don't know how to write 0 in Roman. Do Roman numerals have 0? I don't know. So I say that at step 0, Alice chooses a large prime number p. And announces this p to all of her friends. Okay. And then when I'm doing this calculation, this polynomial is going to be a polynomial over integers modulo p. So all of this is modulo p. Okay. And of course, I have to choose my P large enough so that my secret is smaller than P, but I would normally use a really large P. Like if my secret is, let's say 32 bits, I would probably use a P that is at least 1024 bits. So it's easy to find big prime numbers, just pick a big prime number P. And similarly, when I say here that these coefficients are chosen randomly, they're chosen randomly, but of course my coefficients are also between 0, 1 to P minus 1. Okay. So I have this polynomial of degree T minus 1. I have put my secret as the first coefficient, as A0, and all of the other coefficients were chosen randomly. Okay. Now I want to give shares to my friends. So Alice gives every friend 1 point of this polynomial. So Alice gives the friend phi I, the share Si, and this share Si that is given to the i's friend is just going to be the value of the polynomial at point I, f of I. Okay? So I give f of 1 to my first friend, f of 2 to my second friend, f of 3, and so on. But the secret is f of 0. Okay. That's it. That's Shamir's secret sharing. Now, I want to show that I satisfy these two desired properties. I want to say that if T of my friends come together, they can recreate my secret. Okay, let's see what happens when T of the friends come together. Okay, this is part 3. Suppose that T friends, let's say phi I1, phi I2 to phi IT come together. What is the information that they have? So this friend, this was friend number I1. This friend knows f of I1. So if I just write what they know f of I1. They also know f of I2, right? And so on, and they also know f of IT. So basically, they know T points of my polynomial, right? And we said that this is a polynomial of degree T minus 1. So if we know T points of this polynomial, we can just apply this Lagrangian interpolation and we can find the polynomial. So any T of the friends can find the polynomial f. And when they find the polynomial f, they can just calculate its value at 0, f of 0, and that gives them the secret. So very easy, I can say they use Lagrangian interpolation to find f, and then they find, or they calculate f of 0, which is the secret s. So if T friends come together, they can successfully find the secrets. Now, suppose that I have fewer than K friends, fewer than T friends. So suppose that T minus 1 friends come together. Okay, so if I have T minus 1 friends, they know T minus 1 points of my polynomial. Okay, so they know T minus 1 points of f. So let's say they know this. They know, for example, some point x1 and f of x1. They know x2 and f of x2. Right, so on to xt minus 1 and f of xt minus 1. they know t minus 1 points of my polynomial. And also, none of the xi's are 0, right? Because remember, f of 0 was my secret, and I didn't give this to anyone. I just gave them f of 1, f of 2 to f of n. Okay? So none of the xi's here is 0. Now, I have t minus 1 points, but my polynomial was also of degree t minus 1. Right? Because my polynomial is also of degree t minus 1, I actually need t points to uniquely determine a polynomial. So there is not a unique polynomial that goes through these points. There are actually many polynomials that go through these points. Okay, but this would just suggest that maybe they cannot find my secret, but I want to prove something stronger. I want to say they cannot find any information about my secret. Okay, here's the thing. Suppose that I add a hypothetical point here, and the point that I add here is 0, 0. Okay? So I say the polynomial should go through these t points now. Now I have the t minus 1 points that my friends knew, but I'm also adding 0, 0, and I say the polynomial should go through this. So based on what we just proved, for every t points, there is a polynomial that goes through them. So there is a polynomial that goes through all of these points. And if that was my polynomial, then that would mean that my secret was 0. But if I look at the point 0, 1 with the points that these friends know, this is also giving me t points. So there is also a unique polynomial that goes through this. So if I had chosen that polynomial, my secret would be 1. You see the pattern here. If I use 2, that's the same thing. So basically, they're finding no information about my secret, because no matter what I put here, so let's say I put any value, y, there is a polynomial that goes through this point and also through all of the t minus 1 points that these friends know. So from the point of view of these friends, not only they cannot find my secret, they cannot even rule out one of the possibilities. Like, everything is still possible. Okay, so based on this, I can say that the t minus 1 friends find no information about the secret. They find no info about S, which is perfect. This is exactly what I wanted. Okay, so remember, this was what I wanted in secret sharing. So I said that I want to give shares to all of my friends, and any t of the friends should find the secret, but no t minus 1 friends can find any information, and I proved exactly that. Okay, great. Now we have secret sharing, but let's go back to our original problem. Our original problem was that I have n people, and they want to generate a random number. And we said that each one of our players chooses some value Ri, and then I want to take the sum of these Ri's to be my final random number. But my problem was that I was using a commitment scheme, and I was saying that if someone doesn't reveal, then the whole thing, R or its distribution, can be tampered with, right? So I want to say, if someone doesn't reveal, we will make other people do the revealing. Okay, so this is now going to be my new protocol. Okay, so new protocol, new random number generation protocol. I say that in step 1, every player, so let's say player I, chooses their own random number Ri. Okay, and I'm writing it in red because it's not known right now. And this Ri will be between 0, 1 to m minus 1. And this is chosen uniformly, at least if the player is honest. I might have a dishonest player who doesn't follow the protocol and chooses this Ri in a different way, but I don't care about that. I'm just telling you what an honest player would do. And then we will come back and analyze what happens if someone is dishonest. So every player chooses this. But then I'm going to say that every player does secret sharing. So every player takes the role of Alice in our secret sharing protocol here. So we said that Alice has a secret S. She's sending shares to all of her friends. But here I say that the secret that player I has is RI. So player I is going to send shares of RI to all of the other players. Okay? So player I, this is step 2. Player I sends shares, let's call this Rij of Ri to all the other players, to every player J that is not equal to I. So to everyone else, I send a share. And I have to, of course, also choose a T, because T was, remember, the degree of the polynomial there. So basically, the idea here is that if player I does not reveal, then any T of the other players can come together and they can reconstruct player I's share Ri. Player I's, random number Ri using the shares that they have, the Rij's that they have. Okay. Now, in the next step, player I just does the commitment scheme. So player I chooses a nonce. And does the commitment basically on the smart contract, where the commitment is committing to some HI, where HI was the hash of his random value and his nonce. Okay. So this is the commitment. And then in step 4, they reveal. So each player I does this function call. They do the function call in the smart contract that reveals Ni and Ri. And of course, the smart contract checks that the hash matches. Now, very importantly, there is a step 5. All players make all the shares public. Players make all the Rij's public. And they check if any player has cheated. So when has someone cheated? A player has cheated if they sent, for example, invalid shares to the other players. But how can we find out? We can find out if we realize that the shares that they sent to the different players didn't come from the same polynomial. So when we're doing the reconstruction of the polynomial in our secret sharing, when we're doing the Lagrangian interpolation, if different players can get different polynomials, that means that there was some cheating. Okay, so any player who cheats, any player who has cheated, basically loses their deposit, and also their Ri will not be added to the sum. So in step 6, I would say that my R is the sum of all Ri's modulo M. But this is only the Ri's where player I has not cheated. Okay, and that's my protocol. Now, why does it have the properties that I like it to have? Well, I have this property, of course, which is R is the sum of Ri's. So let's say I have a player who wants to cheat, who wants to tamper with the result or wants to tamper with the distribution of the result. Now, how can they do this? Well, the first thing they can do is maybe they choose this Ri not uniformly at random, but based on some other distribution. But I wouldn't care about this because as long as I have at least one player who's playing honestly and choosing the Ri uniformly at random, my final result will also be distributed according to the uniform distribution. So this kind of cheating cannot happen as long as I have at least one honest participant. Of course, if no one is honest, I don't care at that point and I can't give any guarantees. Okay. Now, the second way that people can cheat is by sending invalid shares. So let's say instead of actually creating the polynomial that they have to create for the secret sharing and then sending valid shares to all of the other players, they're just sending some random garbage, or they're doing something else. They're doing something dishonest here with the shares that they're sending. But this would be caught, right? It would be caught here when all the players make all the shares they received public. And by the way, I'm assuming that whenever there is a message sent between the players, these messages are signed. So if I claim that I received this particular share from you, I can actually prove it. I can also show your signature on it. So if anyone cheats, the other players will find out at this step, and then the value that was contributed by the cheater is not added to the total sum. Okay, why would this prevent cheating? This prevents cheating because if you want to cheat, now you have to cheat at step 2 when you're sending the shares to the other people. But at this step, you don't know anything about the values that the other people chose, about the RIs, right? And because you don't know anything, it doesn't really make sense to cheat at this point because you know that you will be caught later on. You know that your value will not be contributed. And so what's the point? Cheating here is just like choosing your RI to be 0. Just choose your RI to be 0 if you don't want to contribute anything. And additionally, you will lose a deposit. So let's say, again, at step 0, I'm assuming this is step 0 of all of our protocols, that there is a deposit so that we can punish people. So let's say there was a deposit here. Okay. Now, how else can someone cheat? They can say, I don't commit to a hash. In this step, maybe they don't commit at all. Well, if they don't commit, again, we will not add their value to this sum. And it's basically like not taking part in the protocol. And again, they just lose their deposits. They can't really change anything. They can say, I don't reveal. Fine. If you don't reveal in time, remember all of these phases have time limits. If you don't reveal before the deadline of phase 4, that's fine. You will lose your deposit, of course, because you have cheated. But remember, you have already sent shares to the other people. So T of the other people can come together and they can reconstruct your value of RI. And we will add your RI to the sum. So this is actually the sum over all players who have not cheated in their shares, let's say. If you have cheated by not revealing, we will still find your RI value and we will still add it to the sum. So this makes sure that we don't have the problem that we had at the end of the previous session. So no player has the option of saying, I don't reveal. If you don't reveal, you're just losing your deposit. Other people will reveal it for you anyway. So finally, we have a random number generation protocol that satisfies all of the things that we wanted it to satisfy. And of course, you can also check that the miners can't really do anything here. You have to, of course, be careful when you're implementing this. For example, we talked about the fact that you shouldn't have a function that does all of this sum because it uses too much gas and so on. But if you take care of those details, this should work. And also, when you're sending the shares, you don't have to send them on the blockchain. You can just send them by email or privately so that you don't pay gas for sending these shares between the players. Okay. So this is now our new RNG protocol. But very importantly, what should be the threshold T that I use in my secret sharing? Because remember, I said that any T of the friends can find the secret, but no set of T minus 1 friends can find any information. So here's the thing. suppose that some of these players are malicious and they want to collaborate with each other to find other people's secrets. They want to find these RIs, and they want to find it before the time comes, before step 4. Right? Now, I need to make sure that the number of malicious people, the number of, not malicious, the number of dishonest people is at most t minus 1. So now I have this big assumption here. I have the assumption that number of dishonest players is at most t minus 1. Okay. What other assumption did I need? Well, in my step 1, I also needed to have at least one honest player. So the number of honest players should be at least 1. And also, when someone doesn't reveal, the honest players should be able to come together, make the RIJs public, and find the value that was not revealed, right? But in order to do that, I need at least t honest players. So the number of honest players should not just be greater than 1, it should actually be greater than or equal to t. So if you look at this, I have to choose my t so that the number of dishonest players is less than t, and the number of honest players is greater than or equal to t. So a good choice would be just half of the players. So just set t to be n over 2. Okay, so my t can be n over 2. And I'm assuming n is even. If n is odd, you can take this. You can take the ceiling of n over 2. And basically, the idea is that as long as t of the players are honest, this protocol is going to work. But you see, there is a trade-off here. Previously, when I had the protocol with deposits and I said I need $1 million deposits, huge deposits to punish people who don't reveal, I didn't need the assumption that I have half of my players who are honest. The only assumption I needed there was that I have one honest player, because I need one honest player to make sure everything is uniform, right? But now I'm using secret sharing, and for my security, I need a stronger assumption. I need to assume that a majority of the players are honest. But that's fine. I guess in many use cases, you can have this assumption. And if the majority of the players are honest, then this new random number generation protocol would work. And it will give us all of the desired properties that we wanted here. Okay, I'll see you next week.